I am Dr. Narsinga, Professor of Physics, Marri Reddy Institute of Technology and Management. So I am going to teach today the very interesting topic as well as the technology related topic, that is quantum computing. Quantum computing is it's nowadays very popular, as well as it's a very required. What I'm saying is it's a required technology, that is quantum computing. So earlier we use only according to classical only. Nowadays all the computers, most of these computers what we are using, laptops or desktops, all are related to classical mechanics. That means it is not related to quantum. It's only classical mechanics. So here most of our data or whatever we are using, the classical mechanics, it's only the uh, that's we call it as a bits, that is 0 and 1 related only up to now. So that's related one, it will be some type of saturation came into picture, that is around 2015 to 20. It is almost saturated, so that's why we are not getting updated versions of laptops or whatever it is. It will be only I think it's a processor 7 only. I think it's a stop one. So that's a reason why this topic, that is quantum computing, is important. So it will be related to that processor, that what we are using nowadays. All the computers, it will be 0 and 1. That is a bits, we call it as a. So now it will be related to quantum bits. This quantum bits is totally different compared to classical. Classical, we can say it will be one time it will be 0, another time it will be 1 only. So there will be no in between. But in quantum computing, we will get a 0 as well as 1, or we can get both. So these type of phenomenon, it will be related to quantum computing. That's a important means discovery. I can say it will be like quantum computing is useful to make millions of times compared to classical mechanics, according to nowadays computers. So this quantum computing will be much more faster compared to earlier machines. Now what we are using that. So if it is taking 1 day or 2 days, if you make any very big calculations, whereas in quantum computing it will be within short seconds it will be completed. That related things will be, the research is going on still, but we don't. But the quantum computing computer we cannot buy at a time. We cannot buy. So that maybe it will take time to replace our normal laptops, because but quantum computing is very costly affair nowadays. It requires some specific arrangements. So what I am saying is, it's a quantum computing, whatever in that one we use quantum bits or superconducting bits. These all are working under very low temperatures, almost 0 Kelvin. So that measuring that 0 Kelvin is very difficult one. So that's why it is not that much commercialized. What I am saying is, it will be only few quantum computers are working with very big companies like IBM, like that companies. Okay. So this quantum computing and classical computing, that is classical means whatever we are using that one. So this whatever we are using, that quantum classical computing, it depends on Moore's law. Maybe you heard this term, Moore's law. So it will be every 2 years. It means, what I'm saying is, in each I will show you that. Yeah, like this. So it will be every year. It will be increases that number of means transistor or components. So like if you are taking one inch means like a substrate, in that one, some earlier one, it's a 2012, it will be that each chip, each component, it will be around 200 nanometers, around 2012, this one. So around 200 nanometers, but around 2015 this reduced to 10 nanometers. So below the 10 nanometers, it's impossible to make components on this chip. So that's why here you can see the data. Whatever we are saying, that's Moore's law, it will be almost constant because we cannot reduce the component less than 10 nanometers. It's very, very difficult one. So that's why whatever we are using that computers, it will be depends on Moore's law. This Moore's law is nothing but every 2 years it will be double the size. What I mean is the reduce the size of component size, then it will increase the number of components in that chip. Okay, so that's Moore's law. So now this Moore's law is almost end of this Moore's law. We can see here there is a how the trend will be. Okay, so you can see an earlier one around 1950. It will be each component. It will be acting as a 1 centimeter. If you want one transistor or one resistor, it takes almost 1 centimeter area. So 1 centimeter means it's a huge one. That time it will be okay, but later on it will be very huge area. So 1 centimeter taking that component, you take one square inch substrate. So you will keep only few components. So that's why your size of that whatever PCB, whatever you are saying, that one will increase the size. That earlier days around 1950, it will be around 1 centimeter that area. Later on, it reduced to micrometer, then around nanometers. Then now I think around 2020, it should be less than 1.5 nanometer. Then only the components will be working or working with the Moore's law. So, but 1.5 nanometer, it will be very, very difficult. So now it will be stopped around 10 nanometers. Okay. So the 10 nanometers around 2010, it will be almost saturated at that point. So now below 1.5 nanometers to make that component, it will be very difficult. So that's why now there is a requirement that is essential to develop our technology. It requires quantum computing. What I am just showing, like earlier one, you see, if you want to computer first generation one, it requires big room. Later on, it will be only one side, it will be okay in that room. That is second generation. Third generation, it will be only one table is enough. That's the third generation. And fourth generation, like our desktop, these things. Fifth generation, then once again, it will be reduce the size. It's earlier you see that monitor or TVs, you will see the backside very big area. So nowadays, it will be like a paper. That's because of the technology development, because earlier it will be 1 centimeter, now it will be around 10 nanometer, that size will be reduced. So if another further improvement, so maybe you can just check small area only, you will computer will be operated. So that way it's quantum technology, quantum computing may be helpful for us. Okay, you can see the means like generation, how it will be changed. So that's history of the classical mechanics. Okay, classical this one. Then so almost Moore's law. That means it's depends on the size of the computer, whatever it will be. It's a reduced size. It depends on the Moore's law. Okay, so Moore's law, it will be present limit is around 10 to the power of 8 transistor per chip. Per chip means 1 square centimeter. 1 square centimeter, you will components, that is transistors or whatever the BJTs, whatever this one is, we can load up to 10 to the power of 8. That means 10 to the power of 8 transistors in 1 square centimeter. Okay, so that means the typical size of that this one, it will be each component, it will be around 100 nanometers. Okay, so that means we have reached the atomic size, that is 100 nanometer. Maybe another 1-2 years, it will be around 10 nanometers. That is almost atomic size, it will be reduced. So within the atomic size, we cannot make a component. That's a drawback of this classical classical mechanics or classical technology. What I am saying is, so then now you want to make in atomic size the storing in single bit of information, it is almost difficult. So then the quantum effects have become unavoidable dominant. That means if the size of the particle is reduced to nano size, then another phenomenon came into picture, that will be quantum mechanics. So while this quantum mechanics and classical, so it won't work. There will be some problem in reducing the size. What I'm saying is 10 nanometers is okay, but less than that, it will be once again quantum effects will be dominated. So once again, the dominating quantum mechanics, then it will be alternative technology. It should be quantum computers. Up to now, it will be classical. Then quantum computers will came into picture because of this size of nano size of these particles or nano size of these uh, components. Okay, so that's quantum computer came into picture. So what is mean by quantum computer? Then another question will come. That is, it's a quantum computer is nothing but it's an area of computer science that works in uses the principle of quantum theory. Principle of quantum theory, it works. That is quantum computing. But the quantum theory explains the behavior of energy and material and atomic or subatomic levels. That means in nano size, it will be explained this energy and material properties. That is called it as a quantum theory. So quantum computing uses subatomic particles such as electrons or photons. Okay, the earlier one, it will be like electrons, protons only, but the size will be different. Okay, these subatomic particles in quantum computing, it will be useful. So quantum bits are qubits. These particles to exist more than one state. So earlier classical computing, it will be only two states, that is 1 or 0. Here there is a more than one state, that is at a time it may be 1 or 0 at a time. So that's a different phenomenon. That is quantum computing, it will work. That is quantum bits, they call it as. According to classical, you can see only 0 or 1. But in according to quantum, it will be more than one state. That may be 0 or 1 or in between also it will be available. That is quantum bits. That is totally different. Classical bit to quantum bit, it will be different story. So that means the qubit is a two-level quantum system. That means 0 and 1. It may be depend in between also the values will be working. Okay. So in these 0 and 1, there is a once again the Pauli Dirac notations. They call it as a key notation and bra notation, that will come in next sessions. Okay. So this 0 and 1, there is it may be 0 as well as 1 also possible. That we call it as a superposition. That means it may be 0 or 0 1 at a time. So if you see, maybe you just heard about what is that double slit experiment. So if you double slit experiment, if you send the one electron beam, so what will happen? This electron beam, it's a small hole, it is going out. Then it will be distributed in a different energy levels. So this distribution, finally you will get like a wave. So one area it will be maximum, another area it will be minimum. So this maximum minima, it comes because of these waves. It may be constructive interference or destructive interference. So here what happens is the electron going to wave. So that means the dual nature of the particle we can see in a Newton double slit experiment. That's earlier experiment in optical properties. So we can see that electron beam converted into wave structure. So at a time it will be electron as well as wave. So that's behavior, we call it as a dual nature of the particle, dual nature of the moving particle. So that's quantum computing. It will be very important topic, that is superposition, like constructive interference or destructive interference. Okay, so usually if we see that there is a this Max Planck is the father of this quantum physics actually. So it's automatically is quantum computing also. He is not only one person. Quantum physics or quantum mechanics, it may not be one theorem. It is a multiple theorems or approaches. So that's a combination of all these. They call it as a quantum mechanics or quantum physics. So when you change the way you look at things, the things you look at change. That means already we saw in one thing, then that thing may be different in a other direction. So that's what he make one quotation, that is father of quantum mechanics or quantum physics is Max Planck. He is the first person to just observe some of the properties. So that's quantum computing related ones. So it's a Moore's law. This will be like means the size of the components. What I'm saying is the size of the components, it's increasing. So because of that increasing, earlier days we will use very big computers. Nowadays we will use very thin size of the computer screens. So that is related to the component size. This is the Moore's law. So what is this one? Then you can see here this important one. Okay, the classical bit. Classical bit is either 0 or 1. That is in any what I am saying is like differential equations or logic gates. So all computer systems are related to these logic gates. So in that gates we use only 0 and 1. So that is classical bit, we can say. If you make one coin, so it will be one time it will may be 0, one time it may be head or tail, like that. So if you make two coins, then it may be combination of these two also available. That's means the two coins taking this one, it will be quantum bit type. That means it is possible 1 or 0 or both. So like that it will be quantum bit. But in classical bit it will be only 0 or 1. It may be the possible permutations. So if it is 2 to the power of n, whereas in classical bit, whereas in quantum bit it will be 2 to the power of all of, that is only 1, that is only 1 out of 2n possible permutations, whereas in quantum bit it will be all of 2 to the power of n possible permutations. That may be 0 or in between 0. So it depends on the angle. You can see there is a angles also, it will be active. So this depends on these angles, your total spectrum will be changes. This is a classical bit 0 to 1. So if it is a qubit, if it depends on the angle, that is a major important one is angle. So that means around 360 degrees it will change. So it may be not only 0 and 1, it may be in between values also possible. That is a qubit one. So it's the representation is looks like this. So if it is a classical bit only, that we can recognize, that's a cat we can recognize perfectly. But in a quantum one, so it will be in a different directions. What they just represent that quantum bit. Okay. So then that theory or that's evaluation of quantum computing. So where it started. So actually, it's around 1982, Richard Feynman is the advisor to American president. So he given one lecture. So he said at that time, he said there is a plenty of ground in for playing. That is, the term is used for nanotechnology. But nanotechnology is nothing but, once again, it will be quantum mechanics only. Okay, it's a proposed idea of creating machine based on the laws of quantum mechanics. So that time itself is representation. So it will be quantum computing came into picture. So then later on, around 1985, that's David Dutchess developed the quantum turning. So machine showing that quantum circuits are universal. So he's another scientist. So he make a quantum Turing. So machine showing that quantum circuits are universal. So then another person came into picture, that is Peter Shor. He make a quantum algorithm, how to solve these large numbers in polynomial time. So these type of advancement in quantum computing came into picture. So then finally there is one more scientist around 1917. He developed quantum search algorithm with a different complexity. So you can search any, means like our Google search, it will give some different type of things. Like that, they have a searching using algorithms. So that's is Law Grover, this Peter Shor and David Dutch. So is the initial algorithmic means like algorithm developed this one 1985. Then later on they are developed that algorithm into different levels. So that's a foundation where it started, the quantum mechanics. So it's like that. These are the main scientists to make our quantum computing is a little easier. So, but this quantum computing is before that there is a lot of scientists working on quantum physics or quantum mechanics or quantum tunneling, whatever it will be. They all are combined together. These theorems will come into picture. Otherwise, it is not possible. Okay. So this how we can use these applications of these qubits. So if you use means nowadays I think it will be only 10 to below 100 qubits only they are using now. So it's above that it is not at experimentally working on that, but around 10 100 qubits now it is they are working now. So some only few companies are taking that to pitch that instruments. Okay, so I showed in first my this one slide, first slide. You can see there is a instrument like this. Quantum computing machine will be like this. So it will be very low temperature. Lot of connections will be there. So there will be lot of means like what I am saying is connecting one to another. Those this type of things, and it requires lot of different type of scientists required. So some people will be working on mechanical or thermal or like electrical. So many different fields working together. Then only this quantum computing will came means working like that. So that's quantum computing, how it looks to be like that. So here you can see there is a potential applications, but still there is only below 100 qubits only they are using. If you use 100 to 200 qubits, most of the chemistry related formulas or whatever the chemical things, it will be solved using like this. So then optimization purpose we required almost 1000 qubits. So then machine learning, it will be 100,000 qubits. It will be okay to machine learning also. Similarly, for material science problems, they also solve using this. If you want to make 1 lakh, that means almost 100,000 qubits. If you unknown problems also, they can solve. These the key potential applications using quantum computing. Quantum computing based on qubits only. If you are using 1 or 2 qubits, that is also enough to solve means difficult algorithms or difficult problems. They can solve within short time. So that's if you use very high one, then it is the life, or we can say what I am saying is, if there is a medicinal one. So medicinal one, you can choose particular one what requirement. So then this quantum computing will help us to make our lives will be very smooth and easy. Yeah, that is once again that in quantum computing. So the major thing is superposition. Superposition is so major thing in quantum computing. Superposition as well as entanglement. These are the two properties of these particles. It will be means like these only these two properties. Total quantum computing is depends. Okay, the superposition is a sets of qubit apart from classical bit, is that it can be superposition. The properties depends on different properties, it will show you the superposition like constructive and destructive, like that. Okay, so that's in classical physics we have describing a musical tone can be seen as several waves with different frequencies. They are all together is called as a superposed. So that means like what I'm saying is, if a superposition, if one people are working, if so many at a time they are talking, so that sound will be like noisy. So like that, that superposition of one wave to another wave, so it may be constructive, it may be destructive will come. So that's a major important point in a quantum computing. So the superposition is the major one of the major part in quantum computing. Similarly, entanglement. Entanglement means it's two, what I am saying is it will be like twins. If you pinch one fellow, then another fellow will cry. So that's we call it as a quantum entanglement. That means if you change one parameter of one side, then another side also, or far away also, that related one it will change. So that we call it as a entanglement. So that is a correlation between two particles, we can say, or two things, that will be called as a quantum entanglement. So that's thing, superposition and entanglement. So this block theorem and these things. So we will go for next class. Okay. So usually, if you want to study any references, that is quantum computation and quantum information by Niels and Chang. This one will be online book actually. So you can study all the initial basic to technology side. The introduction to quantum computing for non-physicists. There is another survey like quantum mechanics demo also there. So these are the references we can study.